This video covers a really nice cumulative review kind of problem for electricity and magnetism in circuits. What we're given in the problem is the specs on a solenoid, including the number of turns, that's 400, the diameter of the tube the wire is wrapped around, 3.1 centimeters, the length of that tube, 5.2 centimeters. And then we're told this is 32 gauge copper wire. It has a diameter of 0.2 millimeters, so that will allow us to get the cross-sectional area of the wire itself. And we have the resistivity of this wire. So in part A, we want to get the internal resistance of this solenoid, and we're going to have to go back to the formula that relates resistance and resistivity and length and cross-sectional area. In part B, we're going to get the inductance of the solenoid, which depends on the number of turns, the average diameter of those turns, and the length of the solenoid. And then in part C, we're getting the half-life when this solenoid is incorporated into an LR circuit. And in order to get that done, we need the internal resistance of the solenoid that we computed in part A, plus the internal resistance of the battery that we connected it to, and then we'll plug into the half-life formula. So let's get started with part A. Again, this goes all the way back to talking about resistance, resistivity, and the geometry of the wire, the length and cross-sectional area. We know the resistivity, but we still need to get the length. And all we know is that there's 400 turns, and we know the size of the tube that they're wrapped around. So the circumference of the tube will give us the length of a single turn, and then we just multiply by 400. So I'll call it 2 pi times r tube, or RT, times 400. Now the radius of the tube is half its diameter, so I may as well plug in d over 2 and cancel the 2's out in front. And I get pi times the diameter of the tube times 400. Changing the diameter to meters, that's 0.031. And when I run the numbers on this, I get 38.96 meters. What about the cross-sectional area of the wire? So it's very important in this problem to not confuse the diameter of the tube with the diameter of the wire itself. The wire is very thin, that's 0.2 millimeters diameter. Well, the cross-sectional area is going to be pi times the radius squared, and I'll call it RW for wire, so pi r squared. But we can sub in d over 2 for the radius of the wire. And when I square that, I get a factor of 1/4 out in front, so 1/4 pi diameter of the wire squared. Then we need to change that diameter to meters, that's 0.0002 meters, all squared. And when I run the numbers on this, I get 3.142 times 10 to the negative 8 square meters. Now we can plug all the numbers in and get the internal resistance of this solenoid. So we plug in the resistivity, the length, and the cross-sectional area. And I was trying to keep the units on this so we can make sure they make sense. So I have 1 factor of meters canceling over here. 1 factor of meters survives in the denominator, but it cancels the one that was attached to the resistivity units. The only surviving units are ohms, so this is good. And when we run the numbers on this, we get 20.83 ohms. In part B, we want to get the inductance, also called the self-inductance of the solenoid. And I'm just going to quote the formula on this, and I'll post a link to where it was derived. And that's mu naught n squared A over L, where mu naught is called the permeability of free space. N is the number of turns. A is the cross-sectional area of the solenoid itself, so much bigger than the cross-sectional area of the actual wire. And then lowercase l in the denominator there is the length of the solenoid. So we plug all the numbers in. The permeability of free space, 4 pi times 10 to the negative 7. The number of turns, 400 squared. The cross-sectional area of the solenoid itself, I'm going to use 1/4 pi diameter squared again, but the diameter of the solenoid itself is 3.1 centimeters, which we can then write as 0.031 meters, and we're going to square that. All of this divided by the length of the solenoid, which is 0.052 meters, or 5.2 centimeters. And when we run the numbers on this, we get 0.00292 Henries for the inductance. And it's nicer to write this as milliHenries. That's 2.92 milliHenries. Finally, in part C, we want to compute the time for the circuit to reach half its maximum current when the switch is closed. So this is just the half-life for this LR circuit. And we have a standard formula for that, and I'll post a link to where it was derived. That's L over R natural log 2. That's the time for the current to reach half its maximum value. Also, when you turn the circuit off, it's the time for it to get halfway back to 0. And the R in that equation is the total resistance of the circuit. So that's the sum of the internal resistance of the solenoid together with the internal resistance of the battery. So R is going to be that 140 milliohm internal resistance, or 0.14 ohms, plus our solenoid resistance, which was 20.83. And we get a total resistance of 20.97 ohms. And of course, our inductance, we just figured that out, is 0.00292 Henries. So we plug into the half-life formula. And when we run the numbers on this, we get 9.65 times 10 to the negative 5th seconds. And just to place this into units that you would typically see on an oscilloscope screen, we probably want to express this in terms of microseconds. So we'll divide by 10 on the power of 10 part, giving us 10 to the negative 6th, or micro, and then multiply by 10 on the coefficient, giving us 96.5. So I have 96.5 microseconds, and we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.